Thanks everybody for coming to my talk. I'm Jonathan Talmi, and my talk is titled Building a Flexible Data Platform for LLM Training Data. So I lead a team at Cohere called the Data Acquisition Team, but what we really do is we are responsible for building a lot of our pre-training data sets as well as the platform and tooling that help us do that and help other people at the company do that. So today's talk is really going to have three main sections. First, we're going to talk about the science of data for LLMs. So how to think about the role of data in creating really high performance and highly capable LLMs. Then we're going to talk about the life cycle of a pre-training data set, so the common stages that these pipelines go through in order to build out the data sets that make the data usable for training. And then we're going to talk about the Cohere data platform and some of the things we've built that might be really helpful for you as you're building out your own data platform. Before we get started, just to sort of set the, just to sort of educate people in case you're not familiar with the different training phases for LLMs, there's really two main phases. The first is called pre-training, which I'll go into a lot more in the next slide, but you're basically in pre-training, you're creating a really large and really smart base model. And then there's post-training, which you might know as fine-tuning, which is where you build on top of that base model and you create variants that are a lot more easy for humans to use, like chat-tuned models and instruct-tuned models and things like that. So starting with pre-training, pre-training is basically where you train a model in a self-supervised fashion on billions and billions of unlabeled documents. And this is really expensive computationally. It takes months. Can cost tens of millions of dollars or even more. And you end up with a really, really smart, capable base model, but that is kind of hard to use right out of the box because it hasn't been adapted to be used by human beings. So the types of data that you would see during training, that you would include in your pre-training data set are web pages, code files, academic papers, but they're all in sort of raw, unlabeled form. Now, post-training, which is also called alignment, which is also called fine-tuning, is basically when you have a much smaller data set of labeled data and you build on top of that base model and you train it using this labeled data in order to unlock the capabilities of the model and make it a lot easier for humans to use. So for chat, for instruction, tool use, things like that. And the techniques used here are things like supervised fine-tuning, reinforcement learning with human feedback, reinforcement learning with AI feedback. And because the data is a lot smaller, this is relatively computationally inexpensive, and you can do it a lot more often. A lot of places might rerun their post-training pipeline once a week or so. So just to give you an example of the type of data that would go into this post-training data set, you have instruction following, so a prompt and a completion, the user prompt, and then what you want the assistant to answer with. Or multi-turn chat conversations as well, just to help the model learn how to have these long-form conversations with human beings. And I just want to re-emphasize this point. So in terms of the data volumes, at pre-training, as I said, you have billions and billions of documents, which adds up to trillions of tokens. And in human terms, this is, to conceptualize it, this is like tens of millions or hundreds of millions of books. On post-training, data set's a lot smaller. It's thousands, low thousands, high thousands, but not that many documents. Adds up to millions of tokens, and this is like tens of books or hundreds of books. So let's talk about the science of data for LLMs. The most important question is what actually determines the performance and capabilities of a language model? Why have these models become so powerful recently? And that really comes to three factors, the first of which being the model architecture. So this includes the algorithms like a linear transformer or a mixture of experts, hyperparameters you set during training, the choice of optimizer, and then of course you have the compute. So how large is the model that you're training and what resources are you using to train it in terms of the hardware, how efficiently are you using those resources. And then there's the final bucket, obviously my favorite, which is the data bucket. And this is the quantity of your data, the quality of your data, how diverse your corpus is, as well as your choice of tokenizer, which turns your text into tokens and things that the model can consume. So why is data important and how important is it really? Well, very. there's observations from various researchers and from some studies that show that really different model architectures, when they're trained on the same data sets, given enough time and given enough compute, will eventually converge to the same point. And so what this tells me is that performance is really constrained by data more than anything else. Of course, if you're in a compute-limited environment or you're training smaller models, that affects it too. But because the models end up really just approximating their data sets, data kind of sets the ceiling on what your models will ultimately be capable of doing. So data is the secret sauce. And if you're wondering why some models, if some models with similar architectures are vastly different in their performance or capabilities, that really has to do with the data sets, one being more high quality or larger, et cetera. So we're going to talk about the different factors that influence how good your data set is. Well, first is size, which is like the most obvious one. And what we've learned in the last couple of years is that model performance and capabilities actually scale quite predictably with data, parameters, and compute. This is called the scaling hypothesis. So in this example, this is a diagram from the Chinchilla paper, which was building on the original OpenAI scaling laws paper. You're basically able to predict what the ultimate performance of your model will be once you scale your data and you scale your parameters and you scale your compute together. Now, if you are bottlenecked on one of those, then you're quite limited in how much more capable your model can become. So you'll still get some more performance if, for example, you just throw more compute at it, but you don't scale your data or parameters, but there'll be diminishing returns because it's a power law relationship. Now, in practice, recent models like Llama 2, like E34B, and even the Databricks model, which was trained on 12 trillion tokens that was released yesterday, these are trained on way more tokens than what is considered chinchilla optimal. And they continue to see performance gains. The returns are diminishing, but it's just common practice now to train on even more and even more data. So all this means is that if you want larger and more capable models, you need a lot more data. Once we start training models that cost $1 billion or tens of trillions of parameters, you need tons and tons and tons of data. So data set size matters quite a lot. But it's not the only thing that matters. Obviously, you want those tokens to be high quality too. And what do I mean by high quality? I mean clean, coherent, and relevant documents. I'm going to go into this in a lot more detail later on, but generally, you want clean, coherent, and relevant documents. And why does that matter? Well, it means that when you're training, you have faster convergence, your models can generalize better, and there's a higher overall ceiling because there's just more information for the models to absorb, and just more things to learn from, more signal and less noise. And there's some evidence that the scaling laws actually improve when you have higher quality data. So in this example of a paper that used image models, they found that your power law scaling turns into exponential scaling when you improve your data quality. So when you hold out the least relevant or the least informative examples, your models actually get better. And so you can't just sort of just throw more data at the problem. You can even just improve your data quality, and you squeeze out more performance from your data set. Now, the final bucket is diversity. And I want you to think a little bit about why language models have really taken the world by storm over the last couple of years. And that's because language itself is not just a means of communication. It actually encodes very high dimensional information about the physical and the social world. And it's incredibly diverse and incredibly rich. And this diversity of language helps the model learn very robust and generalizable representations about what it means to be human, about our society and the complexities and the higher order concepts and abstractions. So where do you get diverse data? Well, literally the most diverse data set ever created is the internet itself. Starting with GPT-2, we began training on internet data. And the internet is great because it has pretty much, like virtually every conceivable configuration of data of language ever created. If someone's thought it, it's probably on the internet somewhere. So from a grammatical sense, a syntactical, lexical, semantic sense, you just have the most amount of diversity possible living on the internet. But that's not just the only thing that matters. You also want to have other kinds of diversity, like linguistic diversity, domain, like multiple different languages and low resource languages, different domains represented. So having multiple topics and subjects and things that cover a wide swath of ideas and perspectives, and tasks as well. So having instruction following or dialogue or even like chain of thought style data in your data set as well helps the models have a wide range of capabilities. So putting this all together, let's decompose model quality into these three factors. You have your model architecture, you have the compute that you throw at it, and you have your corpus, which is really the weighted mixture of your data sets. Now, your data set can be kind of boiled down into a few factors like your size, quality, the novelty with respect to the rest of your corpus, and strategic relevance. So we're an enterprise company. We want to also train on data sets that cover domains that are relevant to our customers. And so that's an important factor for us as well. And what you should take away from this is that model quality does not necessarily improve with new data. With new data, it may not add much to the model, it may add a little bit, or it may even detract from the model because these other variables matter beyond just the size. And put in a different way, small data sets may be more valuable than large data sets if they're particularly novel or diverse or they're like particularly high quality. So how do we actually evaluate what the impact of a data set is within the pre-training LLM world? Well, we will run ablations, which really just is a fancy word for experiments, training a small model using a different data set configuration or a different data mixture. You train a small model and you run evals on that model, you do some vibe checks, and you generate feedback, and that helps you learn more about what the impact of that new data set or new data mixture did in terms of your model performance and capabilities. If we're able to collect all of this feedback from ablations, from evals, can we actually estimate this equation? Can we then sort of predict what the impact of a data set on model performance will be before we train on it using just the intrinsic properties of the data set, like its size, the quality, which is proxied by a bunch of different metrics that we'll go into later, and its diversity and stuff. Can we estimate this equation? And the answer is kind of. It's not really that simple. You're pretty limited by what you can learn at smaller model sizes. It's not necessarily true that at smaller model sizes, they're not large enough to sort of absorb all the information available in your data. So the behavior might not scale from 1B to 7B to 30, 100B. There's some non-linearities. There's things that you can't really predict, some interaction effects. And then also, of course, we're in a compute-limited environment, so you can't test every single change, micro configuration change that you'd like. You have to be more selective about what ablations you run, but you do sort of learn from the experiments, and you develop intuitions and heuristics, and then you use those to do further prioritization among data sets and opportunities for refining data sets. So this is an active area of science and research, and I'm really excited to learn more about this and to see more research come out. So let's talk about the life cycle of a pre-training data set. What's actually in our pre-training corpuses of the models that you've all come to know and love? Well, if you look at GPT-3, this had around 80% web crawl data, and there was some other data sets that are cleaner and domain specific, like books, Wikipedia, things like that. Going to Llama 1, you see there's also a heavy percentage of web crawl data, Common Crawl and C4, but you also had code data, Wikipedia, books, academic papers. These are like more structured, cleaner data sets, domain specific, whereas the web crawl data is just very noisy and very diverse, but very noisy and middling quality. And a more recent example, the E34B, which is doing pretty well on the leaderboard, This model, again, had 80% web crawls, but a bunch of the other usual suspects as well. So are there commonalities in terms of how we process these really heterogeneous data sources? And the answer is pretty much yes. Most of them will follow the same pattern of ingestion, going on to transformation, deduplication, annotating the data with various metrics and metadata, pruning based on the results of annotation, and then finally ablation and training. Obviously, these steps are, it's not always like this. You may jumble them up. This is super bird's eye view, but generally most data sets will follow this pattern. Starting with ingestion, the most important thing here is to load your raw data without doing any processing, classic ELT type stuff. And so your data might come from various cloud buckets or APIs or web crawls or Hugging Face, but you want to preserve it in the rawest form you possibly can, which permits as much flexibility downstream for doing reprocessing in the future. Now, when you get to the transformation stage, the main idea is to take those raw documents and parse out the purest possible version of a document that you can. So in this stage, you might do things like convert the document format from like a HTML to text, or a PDF to text. And in the process, you're basically doing cleaning as well. So you want to remove any artifacts that are not helpful for training and may actually harm the model. And finally, put these into the format that you want the model to see during training. So this might be Q&A style. Code files might have a specific format that you want, or you might want to keep things in Markdown, etc. And just to give you an example, you can see sort of a web crawl document here. As I said, it's really web crawl document, like on the web pages have a lot of boilerplate, a lot of random stuff on them. So the name of the game is to try to extract the main content and remove all of the navigation buttons, boilerplate, headers, footers, things like that. So you get the purest possible form of that document. Deduplication is really important as well. There's many different types of deduplication that we go through. First is exact dedupe, so you would probably, you just want to remove the sort of exact matches across your training data set. But there's also near deduplication, approximate, so using something like min-hash LSH, you would want to find clusters within your data set of similar documents and pick some threshold, and then also just filter out a lot of those repetitions. You can also deduplicate individual lines or paragraphs or substrings, both within documents and across documents. And then you can also dedupe semantically, which means basically embedding your documents in your training data set and then doing the same deduplication, but rather than doing actual text matches, you're deduplicating on the semantics, the meaning of what each document is trying to convey. And this is essential for web crawl data. As you know, the web has a lot of duplication, a lot of the same garbage repeated multiple times. And just to give you an example here, here are two documents that we found in one of our min-hash clusters, and it's basically just some domain expiry page. And does anyone want to guess how many times we saw this in the training data? Okay, it's a big room. This is not really the best place for audience feedback, but basically we saw this 35 million times. So in one of our web crawl data sets. So it is really not helpful for the model to see this 35 million times. It's probably even actively harmful, and it's certainly not efficient. So you want to remove as much of this as possible. Now, annotation is the next step, and this is where you will basically label documents with various quality metrics, metadata like language, lang ID, toxicity, if you want to do some topic modeling, you can label things with the domain. There's a lot of different things that you want to enrich your documents with here. And I'm going to talk more about quality on the next slide, but I just wanted to sort of explain how I think about this, especially as it pertains to web crawl documents. First and foremost, you want to filter out documents that have ingestion and processing artifacts. So maybe like a conversion from some HTML or some PDF didn't go so well. maybe there's a lot of like HTML leakage or JavaScript leakage or lots of symbols or something. You want to tag these documents and make sure that you don't train on them, because they'll just sort of spike your loss, and it'll be a bad time for everyone. You also want to identify boilerplate and templated content, similar to the deduplication story. So if there's a lot of repetition, ads, social media sharing links, headers and footers, like this is not great, because the model just sees these tokens over and over again, and it doesn't add any value. Coherence is also really important. So, I tell my team, think about the model learning from this data in the same way that humans learn from it. When you're reading a document, it has to be coherent with a narrative structure or clear dialogue or something that makes sense to you. And models are the same way. If you have documents where there's omitted paragraphs or there's lots of jumbled paragraphs or something, it just is confusing for the model and it's just not good. And so you want to remove the most incoherent documents if you can. And then finally is the sort of substance, or like the low value content. Now this is the area where we are extremely careful, and we really try not to be overly prescriptive, right? You do not want to introduce your personal biases into judging the value of the content. So I think this is an area where you want to sort of like be very narrow in your scope, and try to avoid making qualitative or value judgments on what you see. But there is sort of a way that you can say that, let's say, textbook quality data is certainly more valuable than, like, let's say, my inane tweets. They're not really in the same category, but you probably want to have some of both as well. So just take this with a grain of salt. You don't want to be overly prescriptive here. So digging into the quality signals piece a little bit, this is like a pretty active area of research. There's a few different categories that I think about with quality signals. The first is text heuristics. These are sort of the cheap basic signals, like the number of words or sentences or tokens. And it can also be like the presence of certain things within the content, like say a high ratio of symbols or alpha or numeric characters, or even doing some regex pattern matching. As well as repetition. So, especially with internet data, you want to identify documents where there's a lot of repetition within the documents, which is often a good proxy for quality. Now, if you want to get more advanced, then you can use some machine learning or NLP heuristics like perplexity. Oftentimes, people will train a small model on Wikipedia, sort of like a high signal or a good quality data set, and then calculate the perplexity across your data set, and then use that to do some pruning. But you can also have more custom classifiers for things like toxicity, quality, even the subject, the domain. And then there's other techniques like importance resampling, which again, really try to, you pick a target data set or a target distribution, and then you try to map and then you try to calculate the similarity between your source data set and your source distribution and your target distribution. So various techniques to be able to, again, add labels and metadata to your documents. Now, finally, there's LLM evaluators. So you can use an LLM itself to grade the quality, or to do some labeling, or do any sort of signal or heuristic on top of your data. And you can accomplish this through prompt engineering, either zero shot or few shot, or even fine tune a model for a specific task, like doing some grading or labeling. When it comes to pruning, this really just means taking the results of the previous step and doing some combination of filtering and sampling at the document level to produce your final data set. And so, you might want to do some hard cutting off of the worst quality stuff, but then play around with the sampling distribution with the documents that are maybe middle of the road, or it's unclear necessarily what their value add is. So just one case study here from the DeepSeek paper a few months ago. This is their common crawl processing pipeline. And you can see they start on one side with all the raw data, go through text extraction, deduplication, annotation with a bunch of quality signals, and then using that to do document and line level filtering, and they end up with about 7.5% of the original data set which still adds up to billions and billions of documents. So what are some of the challenges as we go through this? The first one I would talk about is that working with web crawl data is just really hard. Super high cardinality, very heterogeneous, and there aren't like clear and established ways to consistently get high value content extractions from web crawls. So they're generally pretty hard to use. And the data itself is pretty large at source. Like it can be multiple petabytes. To some people in this room, that might not seem like a lot, but when you're doing sort of complex operations like deduplication across these data sets, it can be difficult to sort of scale up these workloads to that data size. And then finally, finding the right signals for pruning is very difficult. There isn't sort of a silver bullet when it comes to quality. There's lots of different things to consider because there isn't really a consistent definition necessarily of quality. I think there's still a lot of ongoing research here. So picking the right ways to do your data set distillation is pretty challenging still. Finally, I do want to say that PDFs are a pain in the ass, basically. Definitely a thorn in my side. Really, there is no consistently good way to get quality data from PDFs. There's some interesting projects coming out recently, but if anybody here does have things that they're really excited about in this space, please come find me. I'd love to talk about it. So let's talk about the data platform we have at Cohere. First, we have some different needs than traditional data platforms, certainly different than what I'm used to. You can think of it as us primarily working with unpartitioned, unstructured text and multimodal data. So we don't have really nicely tabular date partition data. We're working with text, and oftentimes there is no natural partition, and that creates some unique challenges, certainly from a data management perspective. And we don't have a need for super sophisticated orchestration. We have pipelines that run semi-frequently because you're not really training these large models that often, maybe a couple times a year. And sometimes you only have to process a data set once. You get like a dump somewhere and you just process it and there it is. There is no sort of continuous ingestion process. The only exception here is for your data acquisition jobs. If you are doing, let's say, your own web crawls, then you may want to run this continuously. We also have a heavy reliance on UDFs because we're doing text processing, whether that's at the text extraction phase or the transformation phase, or if it's for doing like sort of the introspection within documents when doing quality evaluation. There's just a lot of UDFs, and we can't use these really nicely built-in functions that come with like your common APIs. And we also sometimes need GPUs. So if there's a model that you really like that you want to integrate into the pipeline somewhere, we probably have to use GPUs to accelerate that. And that's just very different than what you might do for traditional analytical workloads. Okay, so what are the guiding principles that we have for the data platform? The first is to be as non-destructive as possible when processing data. This is incredibly important. You want to create as much flexibility downstream to be able to remix and reconfigure data sets with new filtering configs, with new signals, new processors, and make it really easy for people to test out these different configurations. So just be non-destructive and preserve as much data as possible. We also want to create reusable components. So if we solve a problem once, if we have a really great converter or a processor parser that we like, we want to turn that into a reusable component in our component library, and so it can be used in all later and future pipelines. We want to simplify and accelerate data quality engineering. This is incredibly important. It should be extremely easy to be able to come up with a new quality signal, add that to our signal library, and then compute that efficiently across data sets of any size. That is incredibly important and gives your users a lot of leeway to experiment. And finally, we want people to be one with the data. This is my mantra. I am a strong believer that the amount of time and the number of eyeballs spent looking at data directly influences the quality of your data. I personally have labeled thousands of examples in the last couple months. And I think the most important thing for anyone, any data practitioner, especially in this space, especially when working with large-scale data, is to just look at the data as much as possible. So any intervention or tooling we can create that helps people do that is great. So this is a little bit of an overview of our architecture. And I'm not going to go into too much depth in all of these different pieces, but I'll talk about a couple of the ones I find most interesting in the next couple slides. We use Spark primarily for the earlier stages of the pipeline when we have a lot larger data to work with. Usually store things in Parquet and GCS since we're a GCP shop. When we get to the quality evaluation stack, we have a signal library where we define signals, compute them across our data sets, and then have tooling to help us sample, look at those samples, and then do dataset-wide analytics. And this is where we might lean more towards like BigQuery because the data's shrunk a little bit and it's just easier to write SQL queries than it is to manage a Spark cluster. Finally, we do index the data to make it easy to search across pre-training data. So I'm going to talk about the quality evaluation piece first. We built a library, a Python package called TextBot, which basically is a signal library that also comes with a scalable compute engine. And it's a pretty simple API. You basically just import an analyzer, you define the config or the signals that you want to calculate, and you pass in some data or you point it at a data set, and it basically returns like the signals and the metrics that you're interested in. And this is really valuable for us because it means that you can go from thinking up a new quality signal to deploying this and computing this on billion plus rows within less than 5 minutes. Obviously not the computation piece, but just in terms of the bring it into the library and then kicking off this job. And we found that this has been really helpful as a way to standardize our signal definitions. And as I said, in order to be one with the data, you need to have great tooling to help you introspect your data and look at documents very closely. We're heavy users of this tool called Lilac, which was just acquired by Databricks. And we worked really closely with their team to help improve some of the features and the layout and fix some bugs. But we are power users of this, and we use it to basically review and label as much data as we possibly can. Strongly recommend this tool to anybody else as well. But Lilac is really just most suitable for samples. And so if you do have the need to do analytics on top of your entire data set and to get distributions for a lot of the things that we care about. So like either the quality signals or other metadata. So we've built various tooling to help us do things like calculating the distributions across your document length and other metrics. And it's really important to generate these analytics across pipeline stages. So you want to see how some pipeline stage, whether it's a processing or a pruning or something, how that's impacted the distributions that you care about. Because it can actually impact things in ways that you don't expect. So being able to have that visibility at each stage is really important. There's some other stuff that's really interesting that we've built. Data lineage tracking with Data Hub, so having better data governance and data management practices. And as I said, indexing and searching across our pre-training data, which is valuable if you want to extract certain slices of the data or see if there's been test set leakage or eval leakage, things like that. So along the way, we've learned a lot, and I'll share a couple of the lessons that were valuable to me as I was sort of building up my expertise. The first is that you should treat training data like code. We introduced a peer review process. So every data set that goes through peer review before we hand it off, which means that if somebody on the team will look through it, look through dozens or hundreds of examples, collect notes, give feedback back, and sometimes we'll have the whole team do it, and we may even do like a bug bashing session together. And now in order to do that efficiently, in order to help people look at as much data as possible without wanting to blow their brains out, you need to make it as frictionless as possible, inspecting, labeling, and visualizing data. And so this means investing in the tooling and the automations that, that mean that you can just go through hundreds of examples and just 10x your ability to look at data. You also, vibe checking is one thing. Vibe checking is helpful, it's necessary, but it shouldn't be the end all and be all. Eventually, you will need to create evals that help you make more data-driven decisions, evals at different stages of your pipeline, so that you can have a more systematic ways of determining how your pipelines, changes in your pipeline have affected your overall quality of the data set that's being produced. So I strongly recommend people to invest in this eval component. And building on that, I think it's also valuable to think about how you can inject intelligence at various stages of your data processing pipelines. So whether it's in transformation or in quality signals or things like that, again, vibe checking, heuristics, these approaches will get you so far, but if you really want to get to the next level, you need to think about how to do things at scale through evals, through more intelligent intelligence systems. And I just want to say shout out to my team at Cohere. Without them, none of this would have been possible. They're great to work with. And if you are interested in this, in the pre-training data world, there's a bunch of open source projects that have great, basically code bases that you can look at, Red Pajama, Data Trove, Dolma, etc. And these will really show you the nitty-gritty of how to build these data sets. Also, there's a good primer out there by a Twitter user named George Jr. Called Datasets of Models to Come that I recommend you check out as well. So that's it. If you like this, you can follow me on Twitter, where I sometimes post about this stuff.